race to win wars and explore the stars, have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. Body armour, saving lives today, but developed on the battlefields of history. The Catapult, the children's toy that has ancient military origins. Wellington Boot, the war hero who inspired the ultimate waterproof boot. We reveal the amazing science and manufacture behind these wicked inventions. Body armour, or forms of it, has been around for centuries. Historically used as a method of protection in battle, body armour today protects soldiers, emergency services, and even civilians.
Now, having body armour has become an absolutely essential part, not just of police work, but also of responding to medical emergencies, so ambulance crews, paramedics, policemen, the military, of course, all wear body armour. But you'll also find journalists wearing body armour when they go to report in volatile conditions.
But where did it all begin? Both the ancient Eastern and Western worlds have records of armour being used that go back thousands of years. Mail was a prominent form of armour and was used for centuries.
Mail is flexible. It's like a material. It's heavy, and it's made of metal and so forth, but a fighter in medieval times wearing chainmail was very difficult to stick a sword into. Equally, you had plate, which is what we think of as a suit of armour. The point of that armour was that it would deflect arrows and it would deflect weapons which chainmail would not. So these are the two extremes of body armour. One is highly flexible, one is highly rigid.
As weaponry evolved, the armour had to evolve with it. As hand cannons began being used in the Hussite wars of the 15th century, the metal of plate armour had to be strengthened to deal with this new threat. Strengthened steel was the metal of choice, and much experimenting with techniques such as heat treating the metal went into creating the most protective armours of the time. Right up until the early 20th century, even in World War I, forms of metallic plate armour were still used in battle. But as technological advances in weaponry continued to be made, innovations in armour and body protection quickly followed. So, what about the armour that's in use today, and how does it actually work?
Modern day body armour works with the view that if you're going to get hit with something, let's minimise the impact it has on the body. If you're going to be shot at by bullets, you'll have different material that's designed to absorb the strength of a bullet and the power from a bullet and spread it over a very, very wide area, as well as having enough of a buffer zone to stop the bullet getting through all the material. You may have a layer or two of Kevlar, you may have a back plate made of metal, and you may also have in between some shock absorbing padding on both front and the back, so that when the bullet hits you, the Kevlar absorbs some of the shock. The metal plate then expands the shock over a much, much larger area rather than a small point area, and the memory foam that may sit behind will absorb the shock and make the impact on your body even less. A triple layer system like this allows you to survive a bullet much more easily.
Body armour has saved countless lives and will no doubt continue to evolve as new threats are developed. Aegis Engineering Limited produce modern personal body armour from their headquarters in Warrington, England.
Aegis was formed in 1990, and for the last 25 years we've specialised in the design and development of unique armour systems for both police and military customers worldwide. Aegis specialises in the design and development of unique armour systems using the latest in materials technology. We utilise materials called aramids or polyethylenes, commonly known as Kevlar or Dyneema. We incorporate these into our armour systems to defeat both ballistic and edge weapon threats.
Once an order has been accepted, each shape used to form the material of the body armour is mapped out in computer-aided design, or CAD software. The computer operator places each piece in turn over the virtual fabric in the software, rotating and moving them as necessary in order to achieve minimal waste, as the fabrics being used are expensive. This process is called nesting, and the computer generates a real-time model showing the placement of each piece, as well as displaying the percentage of efficiency, as well as other important information. The software then outputs a computer file ready to be sent to the respective cutting machine. The designs are also printed on a plotting machine. These designs will give the workers a visual guide, as well as displaying unique numbers for each part. The next process is the laying up of the materials. The fabric spreader lays out a specific length of material as instructed by the information from the CAD software. The material being placed here is for the outer cover of the body armour. The actual armour materials can also be laid here too. The printed pattern will put across the layers of fabric, and it is all moved on to the cutting stage. CNC cutting machines cut all of the fabrics required to form the finished body armour garment. Here the outer cover materials are being cut. The paper top panels stay on the fabric at all times, so that each piece can be tracked throughout the process. The knives of the CNC machine are sharpened often in order to maintain a high level of precision. The armour materials are then manually sorted or kitted into panel sets for subsequent operations such as quilting, tacking, welding and bonding. Careful attention is paid to ensure the correct number of fabric layers and their orientation are used. The kits are stamped with a unique number and passed on. The worker uses a book with guides for each piece. This is to ensure complete consistency. This yellow material is aramid fibre. The aramid fibre has good resistance to abrasion and has outstanding strength to weight properties, and is produced by the American chemical company DuPont. The most important part of this step is to ensure the right number of layers are in each kit.
It can typically take 2 to 3 hours to generate a single piece of armour.
Each of the component materials are then sewn, welded, bonded or otherwise processed to yield a pack of multiple layers of different types of fabrics, which are subsequently put into a cover. The armour panel cover has special labels denoting the manufacturing details, what the pack will protect the wearer from, and importantly, the side of the panel that must face the threat. Once the armour panels and outer covers have been inspected, the body armour covers are fitted with their protective armour panels. Dependent upon the client requirements, there may also be an array of additional items, such as hard armour plates that can resist rifle threats, helmets, pockets, pouches, badges, carry bags and additional equipment that makes up the set of the delivered product. The finished armour is then assembled and then put onto the rack ready for the relevant client. Finished products are routinely taken to be tested using real threats to prove their effectiveness. Now the armour is complete, it can be used out in the field in order to protect the wearer.
Body armour is now an everyday item of wear, worn by security personnel who may face threats in their line of duty. It's also worn by ambulance and fire brigade personnel, and even police dogs have their own armour. Armour can be developed to defeat a wide range of threats. These can be customer specific and can be a wide range of calibers. Plus, we can also defeat stab and spike.
Body armour, truly a wicked invention. The slingshot may be a mischievous children's toy, but behind the cheeky fun lies a military engineering marvel. The catapult.
What one thinks of the catapult is something that hurls a single object, which can be quite small, possibly no bigger than a golf ball, and it can be immense. Like 3 bowling balls rolled into one. Catapults stores the energy imparted by stretching. So it can be, say, a piece of elastic, or it can be a twisted rope, which is going to untwist when you release it. To some extent, a bow and arrow is a catapult example.
The origins of a weapon that could hurl a projectile great distances date back to the military innovations of the ancient Greeks, with an arrow-firing version of a catapult recorded in battle in 399 BC. As this technology was developed and refined, the importance of catapult technology in warfare arguably reached its peak during the medieval period. when catapults and huge trebuchets were used during sieges to try and blast through castle walls.
So you could hurl heavy rocks against their walls or gates, and you could do this with a catapult device. Immensely time-consuming, because spend half an hour winding the thing up or stretching it to get enough energy to hurl a rock hard enough to do some damage when it hit. Alternatively, you could do really unpleasant things like lobbing rotting dead beasts, cattle, into the city. And that encouraged rats, it encouraged all sorts of disease. And so you could undermine the resistance of your enemies by making their lives intolerable.
So, what is the science behind this ingenious weapon? In engineering terms, catapults work just like a lever. A lever consists of a beam that pivots on a hinge or fulcrum. This allows the lever to exert a large force over a small distance at one end, by exerting only a small force over a greater distance at the other. How does this engineering principle affect a catapult? The base of the catapult acts as the fulcrum that the catapult arm pivots on. The entire catapulting process depends on the storing of potential energy as tension in the ropes or wooden arm, or gravitational potential energy depending on the weapon's design. When the arm is pulled back, the rope is twisted and tightens, or the wooden beam bends, or a large weight is lifted into the air which stores the potential energy. When the arm is released, the arm propels forward until it hits the crossbar. When the arm hits the crossbar, the projectile leaves the bucket and launches forward. The projectile is following Newton's first law, which states that objects in motion want to stay in motion, and objects at rest want to stay at rest. The projectile is moving at the same speed as the arm and the bucket. When the arm and bucket stop, the projectile continues to move forward at the same velocity it was travelling before, as it still possesses the kinetic energy from the work done on the arm. Gravity brings the projectile back to the ground, and the combination of its velocity and the gravity acting against it gives the projectile its trajectory.
As time went on, people invented better ways of being nasty to each other, like artillery, which were more effective, and the catapult fell into disuse. But it remained a weapon which could be used in certain circumstances.
One of those circumstances presented itself during 1914, in the trench fighting of World War I. French troops used a form of catapult to launch hand grenades into no man's land and their enemy trenches. Although small mortars soon replaced these antiquated weapons, their use, nearly 2,000 years after their invention, demonstrated how effective the catapult design was. Even today, types of catapults can still be found, with clay targets fired from a type of catapult, and in some navies of the world, aircraft are launched off ships, using a special steam-powered version of the catapult. From ancient heavy weapon to children's toy, the catapult, truly a wicked invention. Here stands an impregnable fortress, a bastion, a mighty castle, and our tester wants to attack. We have seen the principle behind the success of the catapult, but can our man make a mini war machine which is able to attack the tabletop palace using nothing more than everyday office essentials? What do you all need? 6 pencils, a plastic spoon, rubber bands, and some blue tack. To begin, take 2 pencils and lash them together using some of the rubber bands. Take a third pencil and lash this to the other pencils to form a triangle. Another pencil is added to create the bottom of our mini catapult. This pencil needs to be aligned a little back from the bottom edge of the triangle, as this part of the triangle is the fulcrum, and we need to give our beam, in this case the plastic spoon, space to move. Next, carefully slide the top of the plastic spoon between the 2 pencils at the bottom of the triangle. Take a rubber band and loop it over the bottom of the spoon, under the bottom pencil, and then stretch it over the top of the spoon. Then thread this band under the top pencil and back over the spoon again. This creates a hinge, which in itself generates potential energy when the spoon is pulled back. But our tester wants more power. Our tester takes another rubber band and stretches it over the length of the bottom of the pencil triangle. He then pinches the 2 lengths of the band together and uses yet another band to attach them to the top of the spoon. This band now provides even more potential energy, as you can see when the spoon is pulled back. To finish, add 2 more pencils to act as a stand to raise our mighty catapult skywards and leave plenty of room for the travel of our beam. Well, plastic spoon. And for the projectiles, flaming rocks, diseased livestock? Well, no, actually it's blue tack, sculptured into perfect balls of doom. And how does the catapult work? As the plastic spoon is pulled back, the rubber bands are stretched, which generates potential energy. Our tester takes aim and lets fly a shot, the kinetic energy firing the blue blob at our target. And success! Our tabletop war machine smashes down the castle's drawbridge. So, there you go, a fully functioning catapult made with pencils, rubber bands and a plastic spoon. The essential footwear for keeping your feet dry in all conditions, the Wellington boot has become a staple item of everyday life. But this useful boot has a history of military connections. Created at the bequest of 19th century British war hero Arthur Wellesley, the 1st Duke of Wellington, the boot that would carry his name was originally made of leather and was intended as a cavalry boot that could also be worn at society functions. Even though it became popular in 19th century high society, the boot's usefulness skyrocketed when it was married with rubber.
In the 1850s, an American inventor called Charles Goodyear started to develop a vulcanization process, and this meant that rubber could be made as a really durable material, and it was applied to boots, including the Wellington boot style.
In 1851, a pair of vulcanized Indian rubber galoshes were exhibited at the Great Exhibition in London, and soon after, the American Henry Lee Norris founded the North British Rubber Company. This started to make Wellington boots in rubber and would become the leading manufacturer of rubber Wellingtons for the next century.
Now completely waterproof, by 1914 the boot became a sought-after item amongst the hell of the muddy trenches of World War I.
During World War I, the North British Rubber Company, based in Edinburgh, provided over 1 million Wellington boots for the soldiers in the trenches. Keeping soldiers' feet dry was particularly important in the trench conditions of the First World War, where mud and eventually foot rot rendered many soldiers incapable of fighting. Wellington boots were therefore seen as crucial to the war effort because they helped keep the soldiers in the field.
The Wellington boot also served the British Army well during World War II, and in the post-war years its popularity passed from the military to the wider public, and the demand for this mud-bashing boot shows no sign of slowing down.
These days, we still see Wellington boots everywhere. They've become absolutely prolific as a type of footwear. And they're not just used for the countryside, they're also used in the cities just against rain. And they're even a bit of a fashion item. And at festivals, you still see the fashionistas and the celebrities and the singers, and everyone are all wearing their Wellington boots.
The Wellington boot. Truly a wicked invention. Conceived and designed from their headquarters in Somerset, England, Evercreature's Wellington boots actually start life in their factory in China. The boots are made from a compound of natural rubber and carbon silicate, which acts as a filler that gives the rubber its rigidity and durability. This compound is then added into an industrial mixer for 30 minutes. When the mix comes out of the blender, it is still very lumpy and full of air, so it has to be rolled many times for these defects to be eliminated. It is rolled between 2 large metal rollers for 15 minutes and heated slightly to remove all the lumps and air pockets. This is called homogenization. Once the mix is smooth and even, it is laminated between 2 more metal rolls to obtain its final thickness. Here a rubber mix that has different dye is added. The thickness can be adjusted by increasing or decreasing the gap between the rolls. The rubber is then cut into smaller parts for the soles or rolled up and sent for the final thinning process. What comes out is a long thin sheet of rubber. The rubber sheets of the boot are die cut with a metal mould to get various shapes that will be assembled together.
In terms of production, a boot will be made from scratch in a day. So this is quite unusual in any factory. We start in the morning by preparing the raw materials. We will assemble and pack the boots, and everything will be finished in a day. from zero to shipping. We make 600 pairs of boots in a day.
The outsoles are moulded independently from the main body of the boots. Rubber is put inside a waffle mould and vulcanized for 2 minutes. Vulcanization is a natural chemical process that transforms the rubber from being elastic and fragile to a more solid and durable product. Once completed, they are left to cool before being added to the production line. For the main body of the boots, a metal last is used. This is an aluminium shape that represents the inside of the boot. All the various components that make up the boot are applied to this mould. The first step is to wrap the last with a cotton sock, which becomes the inner lining of the Wellington boot. Multiple applications of glue are then sprayed and added on by hand. This will facilitate the assembly of the rubber sheets. Once glued, the insole is added and the moulds can be taken to the production line. Each piece of rubber is then gradually built up. The pieces in black are used for the inside of the boot, for reinforcement and to give comfort.
So if you look at these boots here, you will see that we improved on this foxing. It has 4 different colors. This is one of our trademarks. And this will make the boot particularly waterproof, which is the key function of a wheelie to protect you against water and against humidity. Our outsole here is also patented by us, and it's anti-slippery. So this is also a very interesting design. We improved on the gusset, the extension, which helps you to adapt to any calf. We improved on strap and added a metal buckle, which is more durable than a plastic buckle, which used to break quite easily. We have also at the back a band, which will seal the boot and make them watertight. And finally, we added this molded insole inside, which is made of EVA, and it's ergonomic, so you can wear the boots 8 hours in a day without feeling any discomfort.
The main pieces of rubber that were cut from the die-cut machine are now added piece by piece. Once the boot has come off the production line, they are sent for varnishing, which will give the boot a matte or shiny finish. The boots are then left to dry, so no dripping marks taint the surface. It is now time for the ovens, where the boots can be vulcanized. The boots are placed on racks, inserted into the oven and baked at 200 degrees for 50 minutes. Like the outsoles, the rubber goes through a chemical transformation from highly stretchable to supple and resistant. Fresh from the oven, the boots are hot, but not too hot as they would deform. The last can be removed and recycled for new boots on the line. The upper excess of the boot is removed, checked by quality control and cleaned. All the labels and tags are added and they can now be paired up by size, wrapped into silk bags and placed into their individual boxes. Each box is packed into a carton of 5 and is now ready for distribution. The Wellington boot, truly a wicked invention. So there you have it. A dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing background. Body armour, the catapult and the Wellington boot. All wicked inventions.